All right, guys. Good morning. I guess by the time you're watching this, it should be morning. Um, so first, I want to walk you through the solutions to chapter 24 problems, as I have assigned the homework, and I need you guys to solve it and submit it. So let's dive in. Number two, you're given the electric potential difference between the ground and the cloud. So you can, how do I pick up my writing tool right here? Okay, come on. Yeah, this should work. So you have your, no, I don't like that. Okay, this works. So you have the ground and then you have your cloud, and you need to calculate the, so for this you are given the electric potential difference. That's delta V. Your delta V equals 1.2 times 10 raised to the power 9 volts. What is it you have? What is the magnitude of the change in the electric potential energy of an electron? So you guys know the charge on the electron is an elementary charge. So Q is equal to E. So this electron moves between the ground and the cloud. This electron moves, let's say it moves from here to here or vice versa. And you need to calculate the magnitude of the change in electric potential energy. So you need to calculate your delta U. Well, you're going to start by saying your delta U, one of the equations that you have for delta U is that it is equal to Q dV, where Q is your charge and your delta V is your change in potential. Well, you know Q for an electron is the elementary charge, so that would be equal to E multiplied by dV. Now you can plug in the value of your elementary charge. You guys should know it, and then you can plug in, so you say that elementary charge multiplied by your dV is what you have here. You're given that in your question, so you multiply that value by this and you get an answer. So the answer that you get would be in let's see, would be in electron volts. Well, for it to be in electron volts, you, instead of writing the value for Q here, you just leave it as E. So that would be 1 in this case, 1 multiplied by dV, and that would give you your answer in electron volts. All right, that works. Number 6, when an electron moves from, how do I move this around? I don't know. So when an electron moves from A to B along an electric field line, in this figure, the electric field does some amount of work. So the question is, what is the electric potential difference when it goes from VB to VA? So this is your A, that's your first surface, and then you have your second surface that contains B and C. So we want to calculate the electric potential difference, VB to VA. Let's look at, where's A? This is A, this is B. So VB minus VA for number 6, the A part, VB minus VA, that would be equal to delta U divided by Q. Yeah, so if you are not sure, I mean, you should have this equation, but if you are not sure, just look at this equation on top here and rearrange for dv. So if you have delta u equals q delta v, you rearrange delta u divided by q will give you delta v, and delta v is vb minus va. So that's how we got that equation. Now vb minus va equals delta u divided by q. Remember that delta u though is equal to the negative of work done, so this would be equal to, instead of delta u you can put negative work and then divide by, instead of q, what kind of charge do you have? An electron. So what's the q on an electron? It's just the elementary charge. So this would be this divided by elementary charge, and that would give you, what's your work? Your work has been given here, and your elementary charge is an electron, is negatively charged, so it's negative. These two will cancel out, and which it really doesn't matter because vb minus va would have the same magnitude as va minus vb, but let's keep the signs consistent. So now you have w divided by e. What's your w? 3.94 times 10 raised by negative 19 divided by, what's your e, your elementary charge? 1.6 times 10 raised to power, you figure it out. It's homework, so I can really solve everything for you. All right, so that's the first part A. What about part B? Let's make some space here for part B. Okay, so our part B, VC minus VA. Notice how this is VC. C is located on the same potential surface. Oh no, VC minus VA. So your VC is on this surface, and then your VA is on this surface. So your VC minus VA, just like we did in A, your excuse me, your VC minus VA would be equal to, VC minus VA would be equal to delta U divided by Q. So when you really look at it, it's going to be the same answer as what you have in the A part. What about the C part? VC minus VB. I think we actually talked about this in class sometimes. VB and VC lie on the same potential surface. So this is an equipotential surface, and for that reason, VB minus VC would be equal to 0, because they are on the same equipotential surface. Okay, I think that solves the problems for numbers 2 and 6. And then the next one, to get the next one, I need to change the background. So let's see if I can figure this out. Background right here. Change the background to from the photo library would be this, I believe. All right, let's try that. No, not that one. Why do I have that? Actually, I think it is. Let's try that. All right. Oh yeah, it is. Okay, number 14. For us to solve this, we need to create some space. Sorry guys, I'm really new to this Camo Studio. This is actually the first time I'm saying this, so bear with me. I think it's kind of good. With some practice, I will be able to use it better. All right. How do I change this to black? I don't know. Oh yeah, cool. I think I got it. So number 14. Oops, it's still blue. How do I change this to black? Change to black. Let's do this. Okay. No. Change to black. Okay. I don't know. All right. Let's do. We don't want to use blue. We don't want to use red. We don't want to use gray. Why can I not use find black? This is black. I want to use this. Okay. This is weird. Oh, cool. Got it. Sorry about that. Okay. So, number 14. Consider a particle with charge Q 1.0 microcoulomb at point A at this position right here. So you're given D1 equals 2 meters from Q, and point B, D2 equals 1 meter. So D2 here equals 1 meter. Okay, so you have a charge and you have two positions, position A and position B. Position A is 2 meters away from the charge Q, and position B is 1 meter away. What are we trying to find? If A and B are diametrically opposite each other, what is the electric potential difference, VA minus VB? Okay. So when you think about this, you have one particle and you need to calculate the electric potential due to this particle at A. That will be your VA. So first calculate the VA and then calculate VB, and then you do VA minus VB. Yep, and that will give you your electric potential difference. How do you calculate VA? How do you calculate the electric potential at position A? Well, you use the formula. What's the formula for electric potential due to a point charge? You go through your notes and you should have something that says your V is equal to Q over 4 pi epsilon naught R. Okay, so your VA minus VB will be equal to, you write the expression for Q for VA, and then you minus and you write the same expression for VB. So let's write the expression for VA. VA would be equal to, you have only one charge, so the Q is the same. Q divided by 4 pi epsilon naught. Now your R is the distance from the charge to the point where you're measuring your electric potential. So for VA, your R is D1. Okay, so that would be equal to D1 minus Q over 4 pi epsilon naught. So for your VB, your R will be D2. And that's what you have to do. So when you look at this, remember you can bring these terms out of the equation, and then you're only left with so you have Q over 4 pi epsilon naught, and then in brackets you have 1 over d1 minus 1 over d2. So you can either plug in all of these values, or you can really turn this to kq 1 over d1 minus 1 over d2, because remember from chapter 22 that k is equal to 1 over 4 pi epsilon naught. That's the Coulomb constant. Okay, so you can substitute that, and this will give you your answer. All you have to do now is just plug in all of the values. What is, you can plug in your k. What's your q? You're given your q as 1 microcoulomb. Remember, micron is 10 raised to the power negative 6. So plug in the value for your k, plug in the value for your q, plug in the value for d1, and plug in the value for d2, and you should be able to calculate this. You're lucky that your distances are already given in meters. You don't need to convert that. But for the q, make sure that you convert microcoulomb to coulomb. All right, that's that. If you have any questions, you know what to do. Shoot me an email, and if I have to, I would make a short video just to answer your questions. What do we have for number 25? I actually have to pull the problem up in the textbook because it's not showing very well in here. Remember, I'm still new to this Camo Studio. So that's chapter 24, problems. And what problem is this? Number 25. We should have it somewhere here. Okay, so I have the question. A plastic rod has been bent into a circle of radius r equals 8.2 centimeters. So this is what that diagram you can see very well looks like. You guys have it in your on your blackboard. So that's a plastic rod that was bent into a circle, and the circle has a radius of 8.2 centimeters. Okay, what is it? Has a charge q1. You're given the charge on the ring. Okay. Oh no, this q1 is distributed only along 1/4 of its circumference, and then a charge q2 equals negative 6q1 along the rest of the circumference. So let's take this circle and take 1/4 of the circumference from here to here. Let this have q1, right? Yeah, so that's q1 there equals 4.2 picocoulomb. Remember, pico is 10 raised to the power negative 12. And then, do I want to try this? Yeah, sure. The second part here, the rest of this circumference has charge q2, which is equal to what? Negative 6q1. So 6 times the amount of q1, but it's negative, so that would be negative 6 multiplied by 4.2 picocoulomb. So that's your q2. Now what do we need to find? With V equals 0 at infinity, what is the electric potential A at the center of the circle and B at a point P on the central axis of the circle at a distance D equals 6.71 centimeter from the center? So first you have to measure your electric potential from here. That would be your A. And then next you have to measure your electric potential at the point P on the central axis. This is your central axis. So starting from here, we can place our point P here according to the diagram, and then from here to here is the distance, which is given as 6.71 centimeters. Okay, cool. So you can use the formula for finding the potential due to a circle. What is that formula? I believe the formula is V equals 1 over 4 pi epsilon naught Q1 over R minus Q2 over R. Yeah, because R is the same. So this is ideally R1 and this is R2. But remember, this is both on the same circle. So R1, this will be your R1, this will be your R2. R1 equals R2 equals R. So you can use this formula. Let's see, do you have all the values? All of these are constants. You have the value, that's K. What's your Q1? You have your Q1 and then you have your Q2. So plug in the value of Q1, plug in the value of Q2, plug in the value of R, plug in the value of R, and you can calculate and get an answer for this. This will give you the electric potential at the center. So remember, R is the distance from the charge to the point where you are measuring. Okay, so for the B part, it's asking what is the electric potential at point P on the central axis. So you're going to use the same formula, but let's create some space here. You will use the same formula. The only difference now is your R1 and R2. What's your R1? What's your R2? So it's still going to be the same, but look at it this way. Oops. This is your circle, your central axis. You're measuring from here. So let your Q2 be represented here. You know, this is a circle. So at any point from here, the distance from here to here will be your new R. We can call that R prime. Okay. Now, can you calculate R prime? Of course you can, because you know this distance D, and you know this distance radius R. So you can use Pythagoras theorem to find R prime. When you do that, you just so first find R prime. Your R prime will be equal to the square root of R square plus D square. If I were you, I would work in SI units. So I'm going to convert my D to meters. I'm going to convert my R to meters. So check, you get a value for that. And then for the P part now, at the point P right here, you're just going to write your equation again. That's V equals 1 over 4 pi epsilon naught. Now, this will be Q1 divided by, instead of R, you remember R from the equation is the distance from your charge to where you're measuring, to the position P. So that will be your R prime. So this will be Q1 over R prime minus Q2 over R prime. And when you solve that, you should get an answer, and that answer will be the electric potential at point P. All right, I think that is good enough for the homework problems. If you have any questions, let me know. I'm gonna make another part of this video to actually launch you into the chapter 5.